You are using the computer audio. Okay. Yeah, but where is my... Am I missing something here? Launch meeting, it says. Okay, well, let's click on launch meeting. Open Zoom meeting. Sign in. Maybe I should sign in. Okay, come on. Start video, maybe. Maybe that's what I need to do. Ah, that looks good. Yeah, that looks pretty good. Okay, let's adjust this camera. Uh-oh, that's kind of bright right there. Wonder if I could scoot it over just a tad. Maybe like that. It's still got a bright light there, doesn't it? I don't know. Yeah, now I got two bright lights. I don't know. I think maybe we might have to live with that. I don't know. Okay, let's see. I see a bright light there. Oh, well. It's not the end of the world, I guess. Wonder if we have any students. Let's look down here and see. Nope, it's just me. No students yet. I'm still not happy with that bright light, though. I'll keep playing with that. Hey, I could move this closer. How's that idea? Yeah, let's try that. Let me move this a tad closer. I don't know about that. I'm not too crazy about that. I don't know what I can do about that other than turn it off. Yeah, might be all right. Okay, it's Monday. Class hasn't started yet. All right, I'm just waiting for my students to show up here. It's Monday, August 31st. Yeah. I guess we're ready to go for the dynamics class. And we're going to go over some different terms, I think. Uh, well, there's a few things we could go over there. That'd be good for us. Kind of warm up there. Let's see if anybody showed up yet. Nope, nobody. Well, in 5 minutes, the class is supposed to start. And we're going to go over these symbols here. We're supposed to know the names of every one of those. And we're supposed to be able to sketch them on a diagram. Yeah, absolutely. If we don't know the names and where they are, we're just out of luck. Hey, I've got a wonderful student. Ashley just showed up. Hi, Ashley.
Hi, how are you?
I'm not too bad. I graded some homework. Did you notice that I graded some homework?
Yeah, I saw it yesterday.
Yeah, good. Now I put a little note. Do you get my little notes, my little explanations in addition to the points?
Yeah, I see them.
Oh, good. Sometimes I forget to write in there, and if there's a particular problem that's really bugging you, I could post it if you'll let me know.
Okay. I don't think I have any questions on my homework right now.
You're okay for right now. That's good. Excellent. Most of you students are doing okay on your homework. Hey, look, I've got some more I've got Alex. Hello, Alex. Earth calling Alex. Come in, Alex. And Ryan. And Braxton.
Hello.
Hey, hello, hello. We've got a good class. How about any of you? Ryan, Braxton, Alex, did you have any questions for me?
I don't.
Was that a I don't? Oh,
Correct.
kind of in an echo chamber. I hear sort of a reverberation there. Are you in a tunnel? There's sort of an echo there. Well, we've got a good class so far. We're going to go over these terms in a minute, and I want you to know the names of each one. Why don't we start with that one? What's the name of that? What's the name of that one right there? It's got a name.
Position vector.
That's it. It's the position vector. Now, this is a little different. It doesn't have the vector notation over it. So what's that one?
Magnitude?
It's the magnitude of the position vector. Very good. Excellent. Now this one's kind of weird. It's got the position vector with a dot over it. What's that? We're asking the students what this symbol represents here. You know, our position vector, that's the position, but this has got a dot over it. What does that mean?
First derivative?
Yeah, the derivative. It's the first derivative with respect to what?
Time?
Yes. Yes, it's the first derivative of the position vector with respect to time. And in fact, that's equal to something very important. Do you remember what that's equal to? The derivative with respect to time of position is equal to the, what do you think? Anybody know?
Velocity.
Yeah, it's the velocity. Good going. That's equal to the velocity. That's equal to that one there. See that one there? By definition, really. By definition, that one's equal to the velocity vector. Now this one's kind of weird. It's just got an R with a dot over it. What's that? I don't know if I've shown you that, but you can figure it out. Just look at it. You can tell me what it is. What do you think? Now you know what R is. Somebody told me R is the magnitude. And so what's R with a dot over it? Go ahead. What is it?
Is it the magnitude of the velocity, so speed?
It's yeah, I think you're right. I was going to say it's the first derivative with respect to time of the magnitude of the position vector. But that, you know what that really is like you just said, it's the magnitude of the velocity. I think this here is equal to that there. See it? Is that right? Now let me think. I'm not sure that that's right. I'm not sure that that's right. I am sure that that's the first derivative with respect to time of the magnitude of the position vector. I am sure about that. But I think my excellent student said that that is equal to that. Is that what you said? Who is my fine friend that just spoke up? Who was
Oh,
it?
that was Braxton.
Braxton, are you saying that this here is equal to that there?
Yeah. I if you took the derivative of the vector and then found the magnitude.
It might be, not
Yeah.
let me investigate that. Now I know what the velocity is. There's two ways to write this. Well, there's three ways. You could write it like that, or you could write it like this. Or you could write it like this. And so well, so what? Now I'm getting lost. We were trying to find out what this little guy was. I got a little room here. Let me think about all that, guys. You're doing fine. Now, what's that one right there? That's called the
Magnitude of the velocity.
yeah, it's the magnitude of the velocity. And was that Braxton again?
Yeah.
Braxton, tell me the name of this one.
That's the derivative of the velocity vector.
Yes, it's the derivative with respect to time of the velocity vector. Very good. And it's equal to something. Braxton, it's equal by definition to the what?
Acceleration vector.
Yeah, it's equal to the acceleration. The acceleration is the derivative with respect to time of the velocity. Yeah. Now these here, I never gave you those. That's why we're having a little trouble with them. And I'll have to think about it. I don't want to lie to you. But I do know what that is. It's the first derivative with respect to time of the magnitude of the velocity. That's what it is. But let me think about what those are equal to. I don't think the book ever tells you. Hey, it stormed last night. I could hear some thunder way off in the distance down south. I could even see some little flashes of lightning, not much. And it rained a little bit. But we got to know what these babies are. Now this one here, what's the name of that one? We'll go to my friend here. And let's go to my friend. We're kind of having a review here right now. Hey, William's with us. William, unmute and tell us the name of that little guy right there. We got to know the names. Go ahead.
The unit vector in the radial direction.
That's it. He's got it. Good going, William. As long as I got William. What's that one, William?
The unit vector in the theta or in the angle direction.
Yeah, no, they have a fancy name for it. They call it the transverse. Whoops, I'm running out of room here. They call it the transverse. See, r theta is called the radial transverse coordinate system. That's the name of it. See, there's three systems that we use: X, Y, R theta, and NT. And that's the radial transverse. Now here's the NT. Tyler, I think, is on board. Tyler, unmute. Tyler, and tell me what this U little t is. Do you know what that is? I did see Tyler on there, didn't I? Yeah, Tyler's with us. Tyler, unmute and tell us the name of this little UT. What's the name of it? Worth calling Tyler. Come in, Tyler. Yeah, he's fixing his coffee or whatever. Okay, well, let's pick on, we'll pick on Stuart. Stuart, unmute. Tell me the name of this little guy right here.
I'm not sure. I kept getting kicked out of the class where you talked about this, so I don't quite remember what it was.
Was it your computer or the internet? What do you think the problem was?
I think it was the internet.
Uh-oh. But you're with me now, Stuart. There's an NT system. There's a R theta and there's an NT. Do you know the name of that coordinate system, Stuart? N stands for something that starts with N. What's the name of it, Stuart? What do you think?
Is it normal?
Yeah, that's the normal. And what's the T stand for? You're just not sure, huh? We got to know these, Stuart. It's absolutely important. We got to know them. It's called the tangential. It's the normal tangential coordinate system. We have three different systems: X, Y, and sometimes Z, the R theta and the NT. So, Stuart, what's the name of that unit vector? What do you think?
Tangential?
Yeah, it's the tangential unit vector. And Stuart, what's the name of this unit vector?
Normal.
Yeah, and we got to know the directions of those. Okay, well, let's look at these here. We're having a little review here. If you just turned in, we're going over some of our symbols here that we're supposed to know. This one here, it's a V with a little X underneath it. And let me go to one of my wonderful students here. Ryan, are you with me? Can you help us and tell us the name of this V with this little X underneath it there? What's the name of it?
Isn't it just the velocity in the X direction?
That's it. You got it. It's the x component. It's the x component. See, when they put a little something down below like that, see that little y? That's the y component. You see that little r? Ryan, what do you think this is? This V with a little R down there. Ryan, what do you think is the name of that?
The radial component.
It's the radial component. And I'm picking on Ryan now. He's doing a good job. V with this little theta underneath it. Ryan, what's the name of that?
The transverse component.
It's the transverse component. Exactly. Good going. When you see these little letters here, see that little T? That's the tangential component. Normal component, radial component. And now for a tough one. There's a row sitting there. Let me ask one of my wonderful students, Megan, there's this Greek letter rho sitting right here. What's the name of that, Megan?
Isn't that the radius when you're
It's the radius of something.
curvature?
That's it. It's the radius of curvature. Good going. Okay, well, we did our review. Is there any questions or comments about our little review? Okay. Well, if you don't have any questions, we're going to talk about the radial transverse coordinate system now. And work some problems. That'll be fun. The topic for today is this R theta coordinate system, where the R stands for radial and the theta stands for transverse. The radial transverse, but you know it, you've studied it in school. You guys have been calling that polar coordinates. It's just polar coordinates, that's all it is. Okay, well, let's write the equations now. Now for the unit vector, or for the position vector, it's equal to its magnitude times its direction. And the direction of the position vector, or I mean the unit vector, the radial unit vector is in the same direction as the position vector. Now, if you want the velocity, you have to take the derivative of the position vector by definition. Put 3 lines there. You got to take the first derivative with respect to time. Hope you can read my writing. Now this book, it's too lazy to write that out, so they write it like this. That dot just means the first derivative with respect to time. But see, this is a product. That R changes as the airplane or whatever is moving, and its direction, its radial unit vector changes depending on where this airplane's flying around. They're both changing, they're both variables. And to take the derivative of a product, you have to use the product rule. That kind of makes sense, think about it. If you have a product, R times U of R, and you want to take the derivative of a product, you use the product rule. Okay. You know how that goes. You go R times the derivative of that one plus the derivative of the first one times the second one. And by Jove, you're done. We have just done it. But now this is a little bit tricky. The first derivative of the radial unit vector, I think I'm going to let you read your books for this. I could do it for you, but we got other fish to fry today. If you do that, you'll discover that's equal to it's equal to theta dot it's either plus or minus that, but now let me think just a minute. No, I think it's like I think it's exactly like that. Yeah. You could read your book to see how they get that. Let me show you what page it's on. I'm trying to find that. It's on page it is on page 72. You guys could read this on page 72 in your book and see how they did it. I don't have to show you every last little thing, do I? Okay. Well, then let's write this. I'm going to switch these. That's legal. I can go r dot u of r plus r times theta dot u of r. I hope I didn't lose anybody. No, u of theta. I said the wrong thing. And we're done. Ta-da. We have just written the velocity equation in polar or radial transverse. You can find these in the flap of your book. Only they write it like this. They write it like v sub r. And they write this one as v sub theta. Look in the flap of your book. See if you can find a v sub r, that's the radial component, equal to r dot. There it is, I see it. I'm wiggling my finger right over it. It's right in the flap of my book. What about this one? This is the radial component of the velocity, r theta dot. Let's see if I can find that. By Jove, there it is. V sub theta is equal to r theta dot. There it is. Ta-da. We just got the nice formula for that. Isn't that nice? Okay, so what? Well, let's get the acceleration, and then we'll work some problems. Now to get the acceleration, this is pretty boring. So you might get some toothpicks from the kitchen and prop your eyes open with the toothpicks so you can stay awake during this, because it's kind of dull. Okay, but to get the acceleration, that's just the first derivative of velocity by definition. Put 3 lines there. That's what we're going to do. We're going to get the acceleration now. Okay, well, what we're going to do is we're going to take the derivative of that. We're going to take the derivative of this whole thing. Okay. Well, dang. You know what? We're back to the product rule again. So you're going to have this times the derivative of that plus the derivative of this times that. And then you're not done because, hey, you know what? This is 3 variables. all three of these are changing. And when you take the product rule of, can you take the product rule on three variables? Well, of course you can. What you do is you take the derivative of this one times the other two, plus this one times the derivative of that one times that one, plus this one times that one times the derivative of that one. You can use the product rule on three variables, can't you? Well, let's do it. Here we go. What I'm doing is I'm going to take this first one times the derivative of that one. So it's r dot times u of r derivative plus the derivative of that one times that one. Well, the derivative of that one is r double dot times that one. We just did the product rule on that one. Now we're going to do the product rule on this one. So we're going to take the derivative of that one. That's r dot times the other two. Plus r times the derivative of this one times that one, which will be r times theta double dot times that, plus this one times that one times the derivative of that one. R theta dot u of theta. You have to take the derivative. You wind up with 5 different terms, okay? Now to spare you the ultimate boredom, I'm not going to go into this totally here, but you do need to know, this one and this one. Now this one, let me write it for you. I think I already wrote it and erased it. The first derivative of the radial unit vector with respect to time is equal to the same thing it was the last time I did it. It's equal to that. Now this one here, and that's in your book, it's on page 72. This one here, the first derivative of the transverse unit vector is equal to a negative theta dot times the radial unit vector, and that is on page 73. You could read it in your book, page 72, page 73. And then you do some algebra, you substitute those in, and here's the bottom line. Let's just give you the bottom line. You can do the algebra. You don't need me to do everything. Here's the bottom line. You're going to get an r double dot minus an r theta dot squared u of r plus an r theta double dot plus 2r dot theta dot times the unit vector in the transverse direction. There you have it. This is what you'll get if you'll substitute these into this equation and combine the terms that are the same. And you can find these in the flap of your book. You know what this is? This is the radial component of acceleration. See if you can find it. Go to the flap of your book and look for AR. I'm trying to find it. AR, where the heck is it? I don't see it. There it is. My finger's wiggling there. You can't see it, but here, let me wiggle my finger. it's right here in the book. I'm wiggling my finger. AR is R double dot minus R theta dot squared. There it is. And this here is the transverse component of acceleration. It should be right here, right here. I'm going to wiggle my finger. There. It's in the floppy of your book. It says A with the little theta, that's a component, remember, is equal to R theta double dot plus R plus 2 R dot theta dot. By Jove, it's right there. So now we've shown you where these miraculous equations come from. And you should understand that. It's pretty simple calculus, isn't it? It's time to work some problems now. Do you have any questions about anything? Well, okay, we're going to work some problems now. Let me find one now. I gave you guys a problem, and I want to work one similar to it to help you. It was 12-189. It's on your homework. I'm not sure when it's due, but we got all this, or you can look in the flap of your book. It's all right there. I'm going to erase this and do problem 12-189, unless you have a question or comment. Here's your chance. Okay, nobody said anything, so I'm going to kiss all this goodbye. We're studying the radial transverse coordinate system, which you know as the polar coordinates. And I'm going to help you with problem 12-189. Only I don't want to do the problem for you and spoil your fun, so I'll change something. But we're going to plot this up. Now here's the thing. They have an Archimedean spiral. Doesn't that sound interesting? I bet it was named after Archimedes. Archimedes. Was he the guy that figured out whether a crown was made out of gold or not by putting it in a bucket of water that was full? And that way he got how much water spilled out, and he got the volume, and he knew how much the thing weighed. He had scales back in those days, and he could get the density, and he knew the density of gold, and he could figure out whether is that the guy? Where are my scholars? Is Archimedes? Look at all you wonderful students. We got William and Tyler, Stuart, Shane, Ryan. You guys are smart. You've read stuff in history and all that. Is that the guy? Is Archimedes the guy that did that? Somebody said.
I know the story you're talking about, but I don't remember if it was Archimedes or not.
I don't either. We could look it up. We could Google it. It's okay. Here's the thing, though. He invented, I guess he's credited for inventing the Archimedean spiral. And here it is. It's R equals 8 theta, where theta is in radians. And they're doing this problem in feet. Okay. Well, let's draw the spiral. Now, when you guys do these problems, haven't I preached to you that you're supposed to do it? You're supposed to measure stuff. You're supposed to measure angles and distances. Hey, let me put it this way. Do you carefully measure angles and distances when you draw your diagrams? Or you just make a little tiny diagram about an inch high and just kind of slop it in there and don't pay any attention to the angles or anything? Which would be better, do you think? Let me think. Which would be better? You know, I think it would be better to measure the stuff. What do you think? Well, that's what we're going to do. We're going to measure the stuff. Here goes. Now, let me make a table here of theta. We'll make a little table of theta. This thing's kind of bugging me here. Yeah, there we go. Theta. You know what? We could have degrees, but they want radians. And R. Here we go. We're going to make a little table here. I don't know, maybe 15 degrees, 30 degrees, 45, 60. Well, that's enough. And we're gonna plot this thing up carefully. We're gonna measure it. I got a ruler. Look, we're gonna measure this thing. Okay. But see, we need radians. Now, how do you get from degrees to radians? Well, 15 degrees. See, these are going to be degrees. You multiply by pi over 180, and you will get the radians. Okay. 15 times pi divided by 180. Did you get 0.26 radians? What do you think? Think I might have done that right? 26, you could round it off to 2 or something like that. Hey, we could get R while we got it. We got the radians. Multiply that times 8. I got 2.09. Well, now that would be feet. We're doing this here in feet. Okay. Do I need to explain that, or are you okay? Well, let's do 30 degrees. I know what 30 degrees is. 30 degrees is pi over 6. Okay, let me do that. Pi over 6. I'm getting 0.5236 radians. And now to get the distance, the position vector magnitude, you go 8 times the radians. All right. I got 4.189. I'll just make it 4.19. Now at 45 degrees, I know what that is. That's pi over 4. We know that by heart, 45 degrees. Yeah. Okay, so what's pi over 4? I'm getting 0.7854 radians. And if you multiply by 8, you'll get your distance from the origin. Okay, times 8 is 6.28. 60 degrees. Hey, I know that by heart. That's pi over 3. Okay, pi over 3 times, no, just pi over 3. I'm getting 1.047. And now the distance from the origin, you multiply by 8. You get 8.0 38. Now 75 degrees, I don't know what that is, but see, I can take 75 multiplied by pi radians for every 180 degrees, and I can get 75 times pi divided by 180. I'm getting 1.31 radians. And the distance from the origin would be equal to, multiplied by 8, 10.5, 10.47, something like that. Did I lose anybody? I'll be glad to go back over any of that. Are you okay with that so far? Okay, well here, we're going to plot it up now. This equation right here is the equation for an Archimedean. Oh, brother, I don't know if I spelled that right. An Archimedean spiral. All right, so now we're going to plot it up. Here it goes. And see, this is what you're supposed to do. When you do these problems, you're supposed to make come on now. There we go. You're supposed to make a graph. Yeah, let's make it down lower. I got a feeling I need the room here. Okay. And here's X. Here's Y. And at 0 degrees, we never did put in 0 degrees. But if you put in 0 degrees, you get 0 radians and you get an R equal to 0. 0, and so here you are. Ta-da! You're right there. Now at 15 degrees, you really need a protractor for this. 15 degrees, here we go, 15 degrees. Why don't I just mark these off? See, this is 15. This is 30. This one's 45. This one's 60. And this one's 75. Now let's draw those. Now this one at 15 is 2.09. Why don't I just use inches? That'd be good. So put that right there. You go 2.09. By Jove. We're right there. Now at 30 degrees, we went 0.5236. So I'm going to go 5 inches. 5.2 inches puts me right about there. And then at 45 degrees, I need 0.7854. That's 7.8 inches at 45. 7.8 inches. That puts me right about there. I think. Let me double check that. So yeah, that's about right. And then at 60, I need 1. Well, that'd be 10 inches. Here we go, at 60. So that puts me right here at 10 inches. And then at 75, I need 13 inches. So that puts me right here, 13 inches. My ruler is only 12 inches long. 13 puts me right about there. All right, here goes. Our Archimedean spiral goes like this. Then I ran out of space. Now you're supposed to do this problem at 90 degrees. So you need to make your graph a little bit, because it's going to be up here. Do you understand? It's going to be a little bit taller there. But let me change the problem and make it at 45 degrees. Now 45 degrees is right here. Here's 45 degrees. Now this right here is your vector, and it has a name. It's called the, let's go to one of my wonderful students here. William, I'll pick on William. William, what's the name of that vector that goes from the origin to the body? Here's your body. William, what's the name of that vector there? We're going to call it R with a vector sign. What's the name of it?
It'd be our position vector.
That's the position vector. Very good, William. Position vector. And I tell you how long it is. It's 6.28 feet. These are feet. Of course, I used inches. I measured it as, no, wait a minute. Did I goof up? Uh-oh. 2.09. What did I do wrong here, guys? You know what? I think I put those numbers in. Oh, I got to start all over again. I think I was putting those numbers in. I went 13. Yeah, it's all wrong. Sorry. Let me get it right. I think I had those right. I need these numbers for the R. Somebody out there, please help me stay awake and let me do this right. Okay, now at 15 degrees, we want, I think I did that one right. It was right here. Yeah, that one was okay. And then at 30, we want 4.19. I think I was using the wrong numbers here, guys. 4.19. That puts me right here. 4.19. Yeah, that's about right. And then at 45, we want 6.28. 6.28 puts me right about there. And then at 60, we want 8.38. 60 degrees, we want 8.38. I was using these wrong numbers here. 8.38, that puts me right about there. And then at 75, we want 10.47. Okay, 75 is 10.47. That's right about there. All right, oops. Now we're going to draw this thing correctly. Somebody could have gotten a thank you point just now because I was putting in the wrong numbers. Okay, here comes our spiral, our Archimedean spiral. It goes like this. It goes. I missed that last part. Try that again. There you go. Archimedean spiral, and I did it right that time. And I measured it. I measured it, and I measured the angles. Now you're going to do it at 90. See, 90 would be up here someplace. But I ran out. I only went to 75. And I thought I'd do the problem at 45 degrees. So here, let's do it at 45. Now 45 was this one here. Let me draw that. 45 degrees is right here. There we go. And there's my position vector. And now we're going to put in our, these have names. We're going to put these in now. I like to put them in color. I'm going to put these in red. But where do they go? Where does the radial unit vector go? It's got to be at the body. Now here's my body, do you understand? There's your body. I don't know what it is. Did they ever tell us? Let's read it. Let's see. And a particle. It's just a particle, they call it. It's moving on that Archimedean spiral. It's right there at 45 degrees. That's 45 degrees. But where is the radial unit vector? Well, I know where it is. Do you? Let me ask somebody. What's the direction? Tyler, let's pick on Tyler. Tyler, what's the direction of the radial unit vector? What is the direction of it?
I'm not sure.
That's an honest answer. I love honest answers. Tyler, I'm going to give you a hint. Do you see that little R right underneath it there? That should tell you the direction of that unit vector. Guess again, Tyler. What do you think the direction is if there's a little R sitting right there? Let me help you some more. Suppose you had a vector like this that had a little X underneath it. You know what? That's our old buddy I. All that is the unit vector in the X direction. But here we have a unit vector with a little R underneath it. So Tyler, what direction do you think that might be? He's thinking. See, if you had a little X here, it would be in the X direction. But you got a little R here, so what direction would that be, Tyler?
So it'd be radial, right?
Yeah, it's in the radial direction, but with an R there, that ties it to this R here. See, this is called the position vector, and the radial unit vector, you must know this. It's like that. Do you see it? That's the radial unit vector. It's in the same direction as your position vector. Okay. Now this is the transverse unit vector. Tyler, it's always perpendicular to the radial unit vector. Did you know all these unit vectors are perpendicular? Did you know I and J are perpendicular? I and J are perpendicular. Well, these two have got to be perpendicular too. And the rule is that this one's got to be perpendicular and counterclockwise. Did that show up? Yeah, counterclockwise. Okay, let me draw it for you. Here it is. It's perpendicular. There's your, and it's got a name. I'm picking one last chance, Tyler. You can get this. That thing has a name. It's a unit vector. And what's the name of that unit vector, Tyler? Go for it. The name of it is?
Transverse.
You got it. It's the transverse unit vector. Notice it's perpendicular to the radial unit vector, and it's counterclockwise. Counterclockwise, yeah. Well, there it is. And now we're going to do the velocity and the acceleration. I think that's what they're asking you to do, only at 90 degrees. Let me read this. I got lost, yeah. Sketch the curve and find the radial and transverse components of the velocity and acceleration. That's what we're going to do. Okay. Well, I need a little room here. We did all that, and hopefully you understood it. I need that room. I'm going to erase it. We know how long this position vector is. It's 6.28 feet. Let me make a note of that. I might need that. Okay, I'm going to erase all this because I need the room. Now we have this vector. We showed you, it was pretty boring a little while ago, but we showed you where this equation came from. I think these are what they want. See, you know what that is? That's the radial component of the velocity, and that's the transverse component of the velocity. Now we know what r is. It's 6.28. So I could circle it. But I don't know what theta dot is. Let me read this thing again. Maybe they tell us what theta dot is. They said that they gave us theta dot. Wasn't that nice? They said that theta dot is 4 radians per second. That's what they said. So look here, we know theta dot. Isn't that nice? And we know the direction of the transverse unit vector. There, I did it in red. Did it show up? Yeah. But we don't know r dot. But we know r, and we can take the derivative. See, r dot is just shorthand for dr dt. And when you take the derivative of dr dt, I get 8. How about you guys? Wait a minute. Auga. If you were taking the derivative with respect to theta, it would be 8. But we're doing it with respect to time. So you have to multiply this by d theta dt. It's called the chain rule. I didn't lose anybody on that, did I? I hope not. Or you could just say 8 times theta dot, which is fine. 8 theta dot. And we know theta dot, it's 4. So that's 32. So hey, we got this. Let me write the numbers in here and we'll do it. Here's the velocity. The velocity is 8 times 4, which is 32 in the radial direction. And this is 6.28 times 4. And I don't know what that is, but see, r is 6.28 times 4. If you got lost and you wondered, well, what on earth is he doing now? This is 25.12. What I'm doing is I'm doing problem 12.189, but I changed it. I said, let's do the problem when theta is 45 degrees. See this 45 degree angle right here? That's 45 degrees. You're supposed to do your homework at 90. I thought if I did it at 45, maybe you could do it at 90. Good thinking, maybe? Okay, well, we're done. Ta-da, we got it. Is that what they wanted? Let me read it here. Let's see. Determine the radial and transverse. Yeah, we just did. Only you're not going to find those answers in the back of the book because I changed the problem. I changed it to 45 degrees. They've got the answers in the back. Now, sometimes I assign fundamental problems. That's those F problems. Did you know they have the complete answer for those F problems in the back? So if you don't get a 4 on your homework on the F problems, and you wonder, well, what did I do wrong? What did I do wrong? Well, go to the back and look at the answers in the back for the F problems, the fundamental problems, and you can figure out what you did wrong and figure out why you didn't get a 4, okay? They're back there. Now on this one here, yeah, comment. Go ahead.
Yeah, how did we get 25.12? I got a little lost right there.
Oh, okay. Well, R is 6.28. Remember, we had that table of values and we had R. I can go back over that if you don't know that. It's 6.28. And they gave us theta dot. They said it's 4. Take 6.28 times 4, and it's supposed to be 25, isn't it? Did I do that right? Let me do it again. 4 times 6.28. Well, I got 25 that time. Let me do it again. 6.2. I think I had more numbers here, guys. Times. No, that's right. It's 2512. That's how I got it. Was that my friend Megan?
Yeah, I get it now. I forgot about our chart.
Yeah. Okay, good. Well, we did great. Now let's plot that up there and just see if it makes sense. And we're not done yet. We've got to do the acceleration next. We can do that. See, next we're going to do the acceleration. But first, let's plot this and see what it looks like. Well, in the radial, we're going to go over 32 and up 25. Well, I wonder what kind of scale I should use. Maybe centimeters might work. Let's try that. Okay, if you go 32 in the radial direction, we're right here at our body. 32 puts you right here. And if you go 25 in the transverse direction, I'm doing it in centimeters, that's fine. 25 puts you right here. So therefore, your vector, your velocity vector should be just like that. And in fact, you can get this angle here. I hate to call it theta, maybe we'll call it alpha. The arc tangent of alpha would be the 2512 over the 32. I can get that angle. Let me do that. 2512 divided by 32 arc tangent. 3813. This angle should be 3813 degrees. Well, if you put your protractor on there, and dang, it's about 38 or 40 degrees like we said. That checks out. See, this is called checking your work. And not only that, can you see that the velocity, this would be the velocity. You understand? This is the radial component and this is the transverse component. And when you add them up, you get the velocity. This vector right here is the velocity. And notice that it's tangent to the curve. Did you know your velocity is always tangent to the curve? If you're going down the freeway, here's the freeway. There's the freeway. We'll put some markers on there. Stay in your lane, you know. You want to follow a path that's tangent to the curve. See, that'll keep you on the road. If you follow a path that's not, like maybe it's off like this, you're going to wind up in somebody's backyard. You want to follow a path. You want to follow the road. If the road goes this way, that's the way you want to go. That's your velocity. If the road goes this way, you follow a path that's tangent to the road. Look, we made this diagram, and that kind of looks like it's tangent. That looks like the velocity of this particle. See, he's coming along here. When he gets to here, he's doing that. Interesting. Interesting. Okay, let's do the acceleration. Here we go. Now, let's erase this Broken Arrow Expressway here. And we're going to do the acceleration, but I need some room. Yeah, there's some room in here. Here we go. We're going to do the acceleration now. Now it's a little more complicated. It goes like this. Let's figure out what these are. Now, you know what these are. These are the components. That's A of R. That's the radial component. And this is A with a little theta. That's the transverse component. Okay, well, let's do it. Now, R is equal to 8 theta. And R dot is equal to 8. Well, no. If you were doing it with respect to theta, it would be 8, but we're doing it with respect to time. So it would be 8 theta dot for R dot. But what is R double dot? R double dot would be, wouldn't it be 8 theta double dot? If you took the derivative of that, I think it would. Well, what is theta double dot? They said that theta dot was 4 and it's a constant. Read it. Theta dot is 4, a constant. That's what they said. So what will theta double dot be? Well, it's 0 because the derivative of a constant is 0. So we're off and running. Here we go. Anytime you don't understand something, just speak up. We're doing great. I'll tell you where we are right now. We figured this R double dot out to be 0. Right? Isn't that what we figured out? Yeah. Minus R. Well, what's R? Well, that's the 6.28. Times theta dot. Now, theta dot, they gave it to us, didn't they? Yeah, it's 4. Okay. Oh, wait a minute. You have to square it. See, it's squared. Okay, help me do that. We're going to get that now. What we're getting right now is the radial component of the acceleration. Did you get, holy cow, it's pretty big. It's 100.48 feet per second squared for the radial component of the acceleration. I think that's what it is. I think we did that right. Now let's do the, this has got a name. This is a component. It's called the transverse component of the acceleration. It's the acceleration in this transverse direction. Okay, well, we can do it. We know R. Didn't we decide that theta double dot was 0? See, because if theta dot's a constant, theta double dot's 0. So that's just a 0. So this one is going to be the transverse component is going to be 0 plus 2 times, well, we know what 8 times 4 is. I can do that in my head. 2 times R dot. Isn't that 32? Yeah. Times theta dot's 4, isn't it? Or is it 0.4? No, it's 4. Well, what's 2 times 32 times 4? I don't know. But my calculator does. Holy cow, did you get 256? Okay, here's what I'm coming up with, guys. This is your radial, no. This is your acceleration. We have the radial component and we have the transverse component.
Is the radial component negative?
Absolutely. You're absolutely right. I'm going to give a honking thank you point that goes right here. You are right. Good going. Proud of you. That was Megan, wasn't it?
It's Ashley.
That's Ashley's thank you point. We'll put a happy face by that. There you go, Ashley. Good going. But it's negative. Okay, now let me draw that. Let me show you that acceleration vector. See, we did the velocity vector. Now let's do the acceleration vector. How am I going to do that? Well, maybe use centimeters, I guess. That'll work. Now, in the radial direction, we have 100. Okay, but wait a minute, it's a negative 100. So we'll go a negative 10. Well, kind of goofy, but there we go. Now that's the radial component. And then we have a positive 256. Oh, gee. Bad scale. Bad scale. That's the transverse component. And so if you have these two components, make you a box. You guys all know how to add vectors, right? Here it is. There's your acceleration. What that means is, well, what does that mean? Well, you're going in a curve. Guys, when you go in a curve, you have to have a component of acceleration to the inside of the curve or you're never going to make the curve. See, if you had an oil slick, let's say there's an oil slick right here. You won't keep curving, you'll just go careening off straight. So you've got to have rubber tires on asphalt to keep you in the curve. So I can understand that. But what about I think you have a slight tangential acceleration. I think you're still speeding up a little bit. I think you've got a little bit of speeding up. So you start off here and you go faster and faster and faster, and you're speeding up just a little bit there. We could get the normal and tangential components. All you got to do is figure out the angle here that you have. What was this angle? 3813, and you know this angle is 45. What is 45 and 3813? 45 and 3813 is 8313. And 90 degrees from 8313. If you don't understand what I'm doing, don't worry about it. I'm just showing you here how to get the tangential and normal. 173.13. Okay, let me show you where that is. 173. 13 is right here. This is getting awfully messy. But you know what that is? That's your normal acceleration. Now we know where the tangential acceleration, it's going this way. There's your tangential acceleration. It's in the direction of your velocity. But can you see that the acceleration has an angle with the normal unit vector? That means you're speeding up. Well, I don't want to bore you anymore with that, but that was kind of fun. Now I think you can do that problem. Did anyone have a comment or question on any of that? Nobody has a comment or question. Well, we've got 7 minutes. Let me talk to you about pulleys for a minute. We're going to study pulleys. That's the next section here. Let me talk to you about pulleys. Unless there's a comment or question, I'll still wait and see if anybody wants to ask me something. Okay, well, say goodbye to all this stuff. Say goodbye to the Archimedean spiral. And you're going to do 12,189, only you're going to do it at 90 degrees. I did it at 45 degrees. But it's the same equations. Now, the next topic that we're going to study is pulleys, okay? There we go. Pulleys.
Actually, on the syllabus, after our theta coordinates, it says we're going to talk about dependent and relative motion.
Yeah, see, when you have a pulley
And then,
and you have a body here and a body here. This body, if it goes up, this body will, wait a minute. If this body goes down, this body goes up. They depend. The motion of this body depends on the motion of that body. In fact, for a simple pulley like this, the motions would be equal. It's just that they would be opposite directions. Did that make sense? And now that's my friend Ashley, right?
that was Megan.
Okay, Megan. Yeah, see, if you want to call this A and call this body B, A depends on B, and well, B depends on A. Okay, and that's pretty simple. Now you can see that whatever A does, B does the opposite. But see, you run into slightly more complicated systems. Here, let's do it more complicated. We have 5 minutes. Here we go. We're going to do a more complicated system now. A little bit more complicated, not too bad. Okay, now in this system here, if this is A and this is B, let's say A goes down. Well, B is going to go up. For sure, B will go up. A goes down, B will go up. But the velocities won't be the same. In fact, it turns out that B is going slower. Since it has two ropes on it, it will go slower. Here, I'll draw big arrow there for A, and there's a shorter arrow for B. Megan, does that make sense that B will go up slower?
Yes, I just thought since you said that we were talking about pulleys, that we had skipped the section, but this makes sense.
No, we haven't. We haven't skipped any sections. No. You know, but they have an equation for these called the dependent motion equation. Let me write that. We got 3 minutes left. I'm going to write the dependent motion equation. Now for this one here, it turns out that the velocity of A plus the velocity of B equals 0. Like for instance, suppose A is going down 2 meters a second, and you put a 2 in here, well then V would be minus 2 meters a second. Minus meaning if this is the plus direction, it's going the opposite way. Whereas in this one here, it turns out that the dependent motion equation for this one is V of A plus 2V of B equals 0. And we're going to show you, we'll spend some time on Wednesday showing you why that is. But for instance, if A is going down at 10, then B would have to be minus 5, because 10 plus 2 times minus 5 would give you 0. So the minus means it's going the opposite direction as the A. So it would go up, see, A goes down fast, and B goes up slow. It's called dependent motion. Well, okay, you're going to take a look. I just gave you a preview of that. Pretty interesting stuff. Did anyone have a comment or question on any little thing before we say goodbye? Well, okay. I'm going to say goodbye here in just a second. Unless here's your last chance. Okay, I'll see you on Wednesday then. Bye-bye for now.
But